We're now going to give the proof of the Matroid intersection theorem, which we stated in the previous lecture, and also saw we saw a few corollaries of it. So let me write it. Let me write it again. It says the following: if M1 and M2 are matroids on the same ground set, ground set E, then the maximum size of a set in the intersection of I1 and I2 is, and I'm going to give this a name, Z star is going to be the quantity that is the maximum, is equal to min over all subsets of the ground set of R1 of U plus R2 of E of U complement. So the maximum size is equal to the minimum over all sets of the rank of the set in Matroid 1 plus the rank of its complement in Matroid 2. So let's just to see why this makes sense, or why we think that this might make sense or is natural, we can check that one inequality follows immediately. So this inequality is immediate, and let's just check. So let's take any set I that is an element of I1 intersect I2. And let's take any U that is a subset of the ground set. So, well, what is the cardinality of I? It's just equal to the cardinality of the common elements that I has with U plus all of the remaining elements of I that are not in U. So that's straightforward. But then, because I is in calligraphic I1, and because every subset of I is also in calligraphic I1, then certainly the cardinality of I intersect U is less than the number of independent, the largest independent subset of U, because perhaps it's more than the cardinality of I intersect U. You may have some larger independent subset that is not a subset of I. And similarly for the second term. So what we basically showed is that Z star is certainly less than or equal to the right-hand side for every particular U, and therefore it's less than or equal to the minimization over all U. So what's interesting is for us to now show the reverse inequality. There are a number of different proofs of the Matroid intersection theorem. One of them is based on duality, but for that we need to first give a characterization of the polytope for matrix intersection. So we're not going to take that avenue, and we're also not going to give Edmond's original proof. We're going to give a proof that came a few years later, and it's attributed to Woodall. And it goes as follows. So we're going to prove this, no surprise, by induction. We're going to prove the reverse inequality by induction on the following set. The set of edges, I'm sorry, the set of elements in E. It's too tempting for me to not call them edges when I'm using E and thinking about graphic matroids. The set of elements in the ground set that have rank 1 in both matroids. In other words, that aren't loops in either matroid. So the set of elements E such that R1 of E is equal to 1 and R2 of E is also equal to 1. So this is the base case is immediate, because if the base case would be that this set is empty. So that means if this set is empty, that that we can partition that there are no elements that have rank 1 in both M1 and M2. So we can look at the set of elements that have rank 1 in Matroid 1, the set of elements that have rank 1 in Matroid 2, and you can see that using that, you'll immediately get the result, because let's actually flip back here. We'll see that if we choose U to be that set, then the set of, say, elements that have rank 0 in Matroid 1, then you can see that the first term in the minimization is going to be 0, and the second term in the minimization is going to be 0. So the right-hand side is going to be less than or equal to 0. We know it's, of course, non-negative, so it's equal to 0. And the left-hand side, of course, cannot be smaller than 0, so we get equality. But do the exercise. So, in other words, what I just outlined in words is the base case. Check the base case where this cardinality is equal to 0. So fill in those details. Okay, so we're going to assume that it's greater than 0, and therefore, and also assume my inductive hypothesis is going to be that this holds for all matroids of a particular where this cardinality has a particular size. We'll show it holds for one more. So let's pick some element E that is in this set. We know the set is not empty. So in other words, pick some E with Ri of E is equal to 1 for I equals 1, 2. And now, this is where we're going to use the machinery that we developed in the last 2 lectures, namely contraction and deletion. So let's consider the matroid when we delete E, M1 deleting E, and M2 deleting E. So remember that what is the deletion? The ground set is obvious. It's just E minus E. But what is the independent set for deletion? It's just all independent sets of the bigger matroid that happen to not include element E. So importantly, the rank function doesn't change. So if we consider this, oops, of course I meant 2 here. Clearly, the inductive hypothesis applies. And again, note that for deletion, the rank functions are unchanged. What I mean by unchanged is that if you have a subset that does not contain E, then that subset is equally in M1 and M1 having deleted E, and the rank, whether you measure the rank using the rank of M1 or of M1 deleting E, is the same. That's what I mean by this statement. And we should contrast that with contraction, and where that is not the case. So the rank functions are unchanged, and so now let's ask what happens if this minimum of all U that are a subset of E excluding the ground set excluding this particular element that I've deleted of R1 of U plus R2 of E minus E. So suppose that this happens to be greater than or equal to Z star. Z star is not, I'm not defining Z star with respect to the contraction, with respect to the deletion. Z star is always going to be this value here. It's a value we care about. In other words, and it's the value that we want, that we need in order to show the reverse inequality. So suppose that this is true. Well, because so let's see what the induction inductive hypothesis tells us. The fact that the inductive hypothesis applies on the contraction. So by the inductive hypothesis, I know that in the smaller matroids, I know that in those matroids, this minimization, that value is attained by some set in the intersection of the independent systems for the deleted matroids. So in other words, I know that there exists some I that's a subset of E minus E, and I is in I1 in the deleted matroid intersect I2 in the deleted matroid. But the deleted matroid is the independent sets are just whatever was an independent set in I1 and I2 respectively, and it just happened to not have E. So in other words, this also means that my I is an element of I1 intersect I2. And you can therefore see that we know that that in that case, cardinality of I, this I would be bigger than or equal to Z star. Again, how did we get this? What does the inductive assumption tell us? The inductive assumption, the inductive hypothesis, tells us when it applies, in other words, in the smaller matroid, it tells us that there is some I whose cardinality is equal to whatever this value is here. That's how I got this. So there has to be an I, because we're in a smaller matroid, whose value is equal to this minimization. So if this minimization is bigger than Z star, then that I also has a value that's bigger than Z star. And since we've already saw that I is always less than or equal to Z star, we have equality, and therefore we've proved the inductive step. So therefore we conclude that we must have we can't have this inequality. And what does it mean for that inequality not to hold? It means that this minimization has to have some U for which this is not greater than or equal to Z star. It has to be less than or equal to Z star minus 1. And which U is it? Well, there must be some U hat, which is a subset of E minus E, where this inequality, I'll highlight it, where this inequality is less than or equal to Z star minus 1. So in other words, there must exist some U hat with, just writing down what's on the right here, but plugging in U hat, R1 of U hat plus R2 of E minus U hat less than or equal to Z star minus 1. And I'll put this in a box because we're going to need this, and we're going to keep track of our U hat. So this is something that we're going to need. So this is inequality 1. Let me label that. Oops, no, that's a bad idea. Let's not label it. We'll just remember it. Okay. Now we're going to use contraction. So now let's consider the contracted matroids, M1 contracting E and M2 contracting E. And again, E is going to be, as before, is going to be that same element that we used in the deletion previously. It's the same E. So let me write that down. For the same E, which has rank 1 in both matroids. Now let me remind you that in this case, actually the rank functions are a little bit different, as does independence. So independence is not just all subsets, so they're defined differently. So recall that I is an element of I1 in the, wrong direction, not in the deleted, in the contracted matroid, if and only if I plus E is an element of I1. Now, if you look back to a few lectures ago when we defined contraction and deletion, I gave a simple example of a graphic matroid where I contracted an element and then deleted an element and wrote down the independent sets of in each case, so that we can see that the independent sets are in fact different in those two situations. And also remember that, and obviously similarly for I2, and also recall that the rank function is defined as follows. The rank function, when we contract E, I'll just drop the actually let's do it a little more, make sure the notation is a little more careful. So I'll write it as M1 contract E. The rank function of any set U is equal to the rank function in the original matroid, not with a contraction, of U plus E minus the rank in the original matroid of E. And we know that this last term is equal to 1 by assumption of what E we chose. Okay. In any case, M1 having contracted E, or M2 having contracted E, they have one fewer element in that in the intersection of elements that have rank 1 in both matroids, and therefore the inductive hypothesis applies. So again, the inductive hypothesis applies to both M1 contracting E and M2 contracting E. And so what does that tell us? That tells us that there is an element, that there is a set I. So hence, there exists some I that's in the intersection of, now the notation is going to get a little hairy, but hopefully you'll bear with me, I1 contracting with E and I2 contracting with E. It's a little bit more complicated here because, again, the independent sets are not just the sets that were independent in the original matroid that happen to not have the edge E. They're actually different here. So we need to keep track of this notation. But the fact that the inductive hypothesis applies tells us that there exists such an I whose cardinality is in fact equal to the statement of that minimization that's in the statement of the theorem. In other words, that's equal to the minimum over all subsets of the cardinality of the ground set of the contracted matroid. In other words, E minus E of R M1 contracted E of U plus R M2 contracted. I'm sorry, I'm using the wrong direction. I was writing deletion. Deleting E, contracting E of the complement. But again, the complement in the reduced ground set. Okay, so we know that this is the case. And now, similarly to the previous example, I'm going to assert something about what how large this could be. So my claim is that if this right-hand side that we have, if this is bigger than z star minus 1, then I'm claiming that actually we have found an independent set in our original I1 intersect I2 that satisfies equality, that has z star elements. So let's see why that is. So if the right-hand side is at least z star minus 1, then it's actually immediate, because what does it mean for I to be in the intersection of both of those? Well, by definition, I I wrote this at the top of the page, but let me write it again here. And I'm sorry, this is the wrong direction of my slash. I need to be a bit more careful here. So this means, just like I've written at the top of the page, that I plus E is an element of I1. But this is also true for I2. So let me just make shorthand for I equals 1, 2, and therefore it's in the intersection. And if it's in the intersection, if I has cardinality at least Z star minus 1, then obviously I plus E has cardinality at least Z star. And that is what we need to show. That is the opposite inequality. So we need to consider the remaining case. So what is this? So hence, let us consider the last remaining case, which is that the right-hand side is less than Z star minus 2. What does it mean for the right-hand side to be less than something? It means that there exists some U for which that value is less than Z star minus 2. Same exact idea in the previous slide. So let us name that. So again, what we conclude that that minimization that I had written on the previous slide, M1 contracting E of U plus RM2 contracting E in the complement in the reduced ground set. This is less than or equal to Z star minus 2, which means that there exists some U tilde, which is a subset of E minus E, for which this satisfies this, for which this minimum takes value at least Z star minus 2. In other words, there exists some U tilde. Now we have our U hat, which was in our box 2 slides ago. Our U tilde satisfies that RM1 contracting E of U tilde plus RM2 contracting E in the complement, E minus U tilde, is less than or equal to Z star minus 2. Now let's remember what the rank function does. Again, recall the rank function is not the same in the contracted matroid as it is in the original one, unlike for deletion. So the rank function, this is exactly equal to the rank function in M1 of U tilde minus the rank of the contracted element, which we've assumed is 1. So minus 1 plus the rank function in M2 of E minus U tilde minus 1. And this has to be, again, less than or equal to Z star minus 2, which tells us, again, which gives us this inequality, that R of M1 of U tilde plus R of M2 of E minus U tilde is less than or equal to Z star. It's our second inequality. And recall, I'll put the other one, the other inequality here as well, and we had this from deletion, not from contraction. We had that R of M1 of R U hat plus R of E minus U hat is less than or equal to Z star minus 1. So we're getting close. We're basically going to add these two inequalities. So adding the inequalities, we've got 2 Z star minus 1 is greater than or equal to R1 of U hat. I'm going to use just R1 and R2 instead of RM1 and RM2. Now that I don't have to contract and delete E, I think the notation is clear. R1 of U tilde plus E plus R2, and you'll see why I'm grouping it in this way, E minus U hat plus R2 of E minus U tilde. And now I claim that this is greater than or equal to R1 of U hat union U tilde plus E plus R1 of U hat intersection U tilde plus R2 of E minus the intersection of U hat and U tilde the intersection of U hat and U tilde plus R2 of the complement in E of U hat union U tilde plus E. Now, where in the world did this come from? So think about it for a minute. If you want to pause the video, this proof is bringing together a number of the tools that we have developed in the results. So this comes from the fact that by assumption of how we constructed U hat and U tilde, we constructed them in the deleted and contracted matroid respectively, and therefore E is neither an element of U hat nor of U tilde. And it follows from the fact that the rank functions R1 and R2 are, because they're rank functions, submodular. So it follows from submodularity of the rank functions. So I'll leave this as an exercise for you to just remember what is the basic inequality of submodularity and see that individually both of these inequalities, that these two terms by submodularity are greater than or equal to the sum of these two terms. And similarly, this is the case for these terms are lower bounded by these terms, again by submodularity on R1 and on R2 respectively. Okay, so let's now see where we are, because you see we're actually close because we have some other inequalities. I know that Z star is certainly less than or equal to R1 of U hat intersect U tilde plus R2 of E minus U hat intersect U tilde. This is just the very first inequality that we derived before we started to prove the reverse inequality. So if you look back at the theorem, we said that for any U, Z star is less than R1 of U plus R2 of the complement of U. So in particular, it certainly also holds for U equal to the intersection of U hat and U tilde. And we can also apply it to the union of U hat and U tilde plus the element E that's in neither of them. So I also know that Z star is less than or equal to R1 of U hat union U tilde plus E plus R2 of the complement, E minus U hat union U tilde plus E. But now we see that we have a problem because I guess I've color coded it already. But now if we come up with this, if we sum this, we find that 2z star is less than or equal to all of the terms, these four terms here on the right. So z star is less than those four terms on the right, but the inequality at the top of the page tells us that 2z star is greater than those four terms plus 1. So obviously that is a contradiction. And the contradiction finally concludes the result. So this is again a proof, not the original proof. So this proof is due to Woodall. We will also prove it using LP duality. But for that, we need first a polyhedral characterization of the intersection of the independent systems. And so it's interesting to see what this does for us, what this theorem does for us. In the previous lecture, when we first stated this theorem, we saw that we gave a few corollaries, but I'll just leave this as a slightly more involved exercise, is that we can revisit something that we know is an intersection of matroids. Bipartite matching is a matroid intersection. And therefore, we can think about what this theorem tells us. In particular, what does something like that, the first corollary from the previous lecture, tell us about the situation when we have essentially a perfect matching. So we can use the theorem to rederive or recover Hall's marriage theorem. And I'll leave that as an exercise for you. So we're going to pick this up next time. We're going to move into other aspects of matroid intersection.